Welcome back. In this lecture, we'll explore what is now being referred to as generative AI that primarily revolves around something called the Decoder, which is another framework that's built on the transformer architecture, and in particular, the instantiation in the GPT models, which are a well-known large language model created by a company called OpenAI. So here are our lesson objectives. All right, so earlier we talked about an encoding model such as BERT. And in this case, you have a pre-trained model like BERT, and you have a specific task you want to adapt it to. So you take that pre-trained model and you add some extra layers, you do your gradient descent, you learn the weights for those layers, and you apply it to the application in that way. Now, here's the issue. You still end up needing a whole bunch of labeled data for your target task. The other thing about it is every time you do that, you're making a new model, and those models are very specific for that task. They're not general, which is okay for a given task, but if somehow your task changes down the line, you have to go back, retrain the model with the new weights and so on. There's also some evidence in the scientific literature that this approach results in overfitting during the process of learning those additional weights. And that process, again, is called fine-tuning. So how do we get around this? Well, let's take a step back and look at another result in which the size of the model is compared to the test set. And when we look at things like compute, data set size, and number of parameters, all those things are directly related to how well the model performs. So as we see the loss in a test set with these very large neural approaches gets lower and lower just by throwing more data and more parameters at the problem. And the study that showed this illustrated that these factors are much more closely related to the accuracy of the model as opposed to other things such as the architecture. Now, can we use this idea to maybe create a more generalized model and somehow get away from this fine-tuning process that, as you saw in the previous slide, leads to things like possible overfitting, having to go through gradient descent multiple times for each use case you have, and so on. And so if we have a very large model, and we're talking models with billions of parameters now, and we train it on a task where it can predict, future words in a sentence or a conversation, can we use this in other things and avoid this fine-tuning process? And the answer is we can. We do it with what's called prompting. And to get a little bit of a glimpse as to how these decoder models differ from the encoder models, consider BERT. Encoder architecture, it uses this bidirectional relationship. So when it masks a word in a sentence, when that is done, it's predicting that word based on both the words that come before and after. And this masking occurs on the input. So it's almost like with that self-supervised process we described, we are essentially turning a regular data set into a label data set where the labels are, in effect, the masked words. GPT, which is a decoder architecture, we're looking at something a little different. Here now we have only unidirectional relationships because we only want to predict the words that are coming in the future. And here the masking is actually integrated into the softmax layer of the attention head. And it's these ideas that lead to generative AI because now we're predicting words that are in the future, not based on anything that we have maybe prior knowledge of what comes after those words, only what comes before. And so let's give an example. Consider this input. We've tokenized this sentence, my dog loves food, and we have a start and end token as well. And then what we want to do is that goes into a decoder. And then the desired output is everything that's one position to the right of it as you read it. So the start token maps to my token maps to dog, and so forth. But it's more than just that token in the input mapping to the corresponding position of the output. The output token can also depend on everything that came prior. So we see that, for example, with dog, we have a dependency coming from both the start token and the my token. By the time we get all the way to food, we have dependencies coming from everything else. Whereas when you look earlier on, my only stems from the start token. So the decoder architecture, when you look at kind of a high-level view, it looks very similar to the encoder architecture. However, the key differences, come up in one, this unidirectional dependency, and two, masking within the attention head. Here, the masking occurs in the attention head in a way to enforce this unidirectional flow of information. So you might hear a lot about what's called a large language model or a foundational model. And this is referring to large models that are trained in this fashion using this decoder framework. GPT in particular, that's OpenAI's LLM. And these things are very expensive to train. They often cost upwards of tens of millions of dollars. And as a result, the expense incurred by training, as well as the sheer size of it, is normally you're not going to access these models in a direct fashion. Rather, you're going to leverage an API. Now, this is a purely black box thing, not only just in the typical way we talk about a neural model being black box in general, and that it's hard to make sense of all these weights, but we also don't know what changes a company like OpenAI is making to the model behind the scenes. If they, did they retrain it the other week? Did they make certain implementation changes that cause it to provide different results for a given input? And, the best you can really hope for is that you'll have updated documentation from the vendor. You don't have that control that you do with something like a BERT model. But the trade-off is we can use this model in a way that avoids fine-tuning, which is actually quite powerful. So that's the introduction to the decoder architecture. Stay tuned and we'll explore more topics related to this soon.